Welcome to the pH calculation tutorial. In this tutorial, we're going to cover several different pH calculations. We're going to calculate the pH of some acids and we're going to calculate the pH of some bases. In addition, we'll take the pH and then calculate the concentrations of either hydrogen ions or hydroxide ions. To do this, we're going to have to remember some of the things that we learned in the previous tutorial on concentration, using the kW expression and so forth. As with the previous tutorial, we are also going to have each question introduced with some focus ideas and then wrapped up with some concluding thoughts and some questions for you to think about. In this first problem, we're simply going to calculate the pH from a known concentration of hydrogen ions. To do this, I'd like you to focus on a couple of things. I want you to focus on the new rules for significant figures when you use an equation that has a log function in it, and I'd like you to consider the use of units in this equation. What is the pH of a solution with a hydrogen ion concentration of 1.0 times 10 to the negative fifth? The first thing we need to do is identify the hydrogen ion concentration given to us in the problem. We have that the hydrogen ion concentration is 1.0 times 10 to the negative fifth molar. And as you can see, I went back and added the capital M for molar in the top of the problem. Next, we're going to need to identify the equation for pH. As you can see, the pH is equal to the negative log of the hydrogen ion concentration. This pH equation works for any solution and works for any situation where you have the hydrogen ion concentration. Next, we substitute the hydrogen ion concentration into the pH equation. You can see that we now have the pH equals the negative log of 1.0 times 10 to the negative fifth. When we put this into our calculator, we get that the pH equals 5. Let's take a look at the significant figures. Here we have that the pH is just equal to 5, no decimal point after that. This is because we can only have one significant figure. The reason we can only have one significant figure is because in the hydrogen ion concentration, we only have one place to the right of the decimal. The rule for significant figures for the pH calculation using the negative log is the number of significant figures in the pH equals the number of significant figures to the right of the decimal of the hydrogen ion concentration. Now that we've completed the problem, I want you to think about the log equation that is used for pH. This is a log base 10 equation. What does a log base 10 equation mean? In this next problem, we're going to calculate the pH of a strong acid. I want you to focus on the use of stoichiometry and the ionization equation so that we can calculate the concentration of the hydrogen ions and then calculate the pH. A solution of hydrochloric acid has 7.2 grams in 1.0 liters. Calculate the pH of this solution. As you can see that this problem is going to be a little bit more difficult than the first problem. That's because the hydrogen ion concentration is not given to us directly. We'll first have to calculate the hydrogen ion concentration before we can use the equation for pH. To do this, we need to realize the fact that hydrochloric acid is a strong acid. Therefore, it completely ionizes in solution, yielding hydrogen ions and chloride ions. From there, we're going to have to use stoichiometry. We start with the fact that we know that there are 7.2 grams of HCl. We multiply this by 1 mole of HCl over the molar mass of HCl, which we get from the periodic table, 36.5 grams, times 1 mole of hydrogen ions for every 1 mole of HCl. And this ratio comes from the fact that it's a completely ionized strong acid and giving us a 1-to-1 mole ratio. After we do the math, we find that there are 0.20 moles of hydrogen ions in this solution. The next thing we're going to have to do is calculate the concentration of hydrogen ions from the moles that we just determined. Okay, so to solve for the hydrogen ion concentration, we take the 0.20 moles and divide them by the 1.0 liters of solution that are given to you in the problem. This, of course, gives us 0.20 molar, capital M for molar. Now that we know the hydrogen ion concentration, we're all set to use the equation for pH. And here it is. The pH again equals the negative log of the hydrogen ion concentration. Here we substitute in the 0.20 molar that we just calculated from the stoichiometry. And again, because the pH is a unitless number, we put the number into the equation without units. Finally, we do the math, and we get that the pH is equal to 0.70. Here, we have two significant figures because the hydrogen ion concentration had two places to the right of the decimal. Now that we've finished the problem, let's think about the pH scale. The answer to this problem, the pH equals 0.70, what does that mean? Is that a very acidic value or is that a very basic value? Well, if we remember the pH scale goes from 1 to 14, and then a neutral solution is at a pH of 7 right in the middle, the acidic area is on the bottom half of the pH from 1 to 14. So a value of 0.70 pH is actually very, very acidic. In fact, the pH scale extends past 1, or extends less than 1, and also extends past 14. Most of the time, it does land between 1 and 14, but as we can see in this case, it sometimes doesn't. In this next problem, we're going to calculate the pH of a base. It's actually going to be a strong base. So before we start the problem, I want you to consider what the pH value should be for a strong base. Thinking about the pH scale going from 1 to 14, and that a neutral solution is at a pH of 7. I also want you to focus on the use of the Kw expression. This is the first time we've done this since the last tutorial. Calculate the pH of a 0.005 molar potassium hydroxide solution, KOH. First of all, you might be thinking to yourself, this is a strong base, and strong bases don't give us a hydrogen ion concentration, they give us a hydroxide ion concentration. You can see this from the dissociation equation for the KOH. It dissociates into potassium ions and hydroxide ions. Because it is a strong base, it is a complete dissociation. We can see from the dissociation equation that the ratio between potassium hydroxide and hydroxide ions is 1 to 1. Therefore, we can see, and this is being typed up as we speak, therefore we can say that the concentration of the potassium hydroxide is the same as the concentration of the hydroxide ions. It's a 1 to 1 ratio. Therefore, 0.005 molar KOH is equal to 0.005 molar OH minus. Well, now you might be saying to yourself, well, that's great. We have the hydroxide ion concentration, but how do I get to the hydrogen ion concentration to calculate the pH? We have to remember what we learned in the last tutorial. Anytime we have the hydroxide ion concentration, we can calculate the hydrogen ion concentration using the Kw. We take our expression for Kw, hydrogen ion concentration times hydroxide ion concentration, and we algebraically rearrange it to solve for the hydrogen ion concentration. This gives us that the H plus concentration equals Kw divided by OH minus concentration. We substitute the value for Kw, which we have memorized, 1.0 times 10 to the negative 14th, and we divide that by a unitless concentration for the hydroxide ion. We do the math, and we get that the hydrogen ion concentration equals 2 times 10 to the negative 12th molar. Notice that because there was only one significant figure in the molar concentration of the potassium hydroxide, we can only have one significant figure in the hydrogen ion concentration after we use the Kw to solve for it. Now that we have the hydrogen ion concentration, we can substitute that into the equation for pH. We have that the pH equals the negative log of 2 times 10 to the negative 12th, and when we do the math, we get that the pH equals 11.7. Again, because Kw is unitless and pH is unitless, you don't have to put the concentrations into either of those equations with any units. Here, we have three significant figures in the value of the pH, 11.7. We know that we're going to use three significant figures because we only have to have one place to the right of the decimal because there's actually only one significant figure in the hydrogen ion concentration. So because there's one significant figure in the hydrogen ion concentration, we only have one significant figure to the right of the decimal. But because we also have 11 at the beginning, it just turns out that that rounds off to three significant figures. I know it's a little strange, but you just have to keep in mind that the rule is the number of significant figures in the hydrogen ion concentration equals the number of places to the right of the decimal of the pH. Now that we've completed the problem, let's take a look at the answer. The pH equals 11.7. Does that make sense? Does that make sense for this strong base? I want you to ponder that before we move on to the next question. In this next problem, we're going to move in the opposite direction. We're going to be given a pH value and have to work backwards to solve for the hydrogen ion concentration. In this problem, I'd like you to focus on the algebra that is needed to convert the pH equation to rearrange and be solved for a hydrogen ion concentration. Okay, calculate the hydrogen ion concentration in a solution with a pH of 2.34. As you can see, this problem's a little bit backwards. Or not a little bit backwards, it's completely backwards. In this case, you're given the pH and you need to solve for the hydrogen ion concentration. And there you have it, the pH is given, it equals 2.34. So how do we work backwards? Well, we need to take our equation for pH and do the inverse log to solve for the hydrogen ion concentration. The algebra on this is a little bit tricky, so I'm just going to give you the equation. So you can see, if we start with the pH equals the negative log of the hydrogen ion concentration, H+, when we rearrange it using the inverse log, we have that the hydrogen ion concentration equals 10 to the negative pH. From here, we just substitute the fact that the pH equals 2.34, so we have that the hydrogen ion concentration equals 10 to the negative 2.34. We do the math in our calculator and we get that the H+ concentration equals 4.6 times 10 to the negative third molar. Alright, let's take a look at the fact that we had to add the unit molarity at the very end. Again, because pH is a unitless number, there's no units in the equation. But because you're solving for an H+ concentration, we do need a unit because concentration has the unit of molarity, capital M. Also, let's take a look at the significant figures. Alright, because there are two places to the right of the decimal in the pH, the 0.34, there has to be two significant figures in the hydrogen ion concentration, which gives us the 4.6. Now that we've completed the problem, did you understand the algebra? Do you think you'd be able to solve for the hydrogen ion concentration in the pH equation on your own without just remembering what we did here? Now we're going to calculate a pOH. pOH is calculated very similarly to pH. In this case, we're going to calculate the pOH of a strong base. You could actually calculate the pOH of an acid, a strong acid or a weak acid, just in the same way that you can calculate the pH of a base. Also, before we start the problem, I'd like you to think about the fact that this is a strong base and to consider where the pOH value should be on the pOH scale, being converse to the pH scale. What is the pOH of a 3.0 molar calcium hydroxide solution, Ca parentheses OH parentheses 2? As you can see in this problem, we're not calculating the pH, we're trying to determine the pOH of a strong base. Because calcium hydroxide is a strong base, it completely dissociates into calcium 2+ ions and then in this case 2 hydroxide ions. So we can see that the mole ratio of calcium hydroxide to hydroxide ions is 1 mole to 2 moles. And this is going to be important when we take a look at our stoichiometry. And here is the stoichiometry. We start off with the fact that we can break down the 3.0 molarity into 3.0 moles of calcium hydroxide over 1 liter, because that's what molarity means, the number of moles over the number of liters. That's our first fraction. Next, we take a look at the mole-to-mole ratio between calcium hydroxide and the hydroxide ions. As we said before, the ratio is 1 to 2. So in our next fraction, we have 1 mole of calcium hydroxide on the bottom of the fraction and 2 moles of hydroxide ions on the top of the fraction. When we do out the math, we get that we have 6.0 moles of hydroxide ions over 1 liter of solution. The liters never got canceled out by anything. Well, if we have 6.0 moles of hydroxide ions divided by 1 liter, that means that the concentration of hydroxide ions in this 3.0 molar calcium hydroxide solution is really 6.0 molar. which is obviously twice as much as the 3.0 molar. Alright, so there's our hydroxide ion concentration, 6.0 molar. Next, we're going to have to use the equation for POH. The POH is calculated in the exact same way that the pH is calculated. In this case, we have that the POH equals the negative log of the hydroxide ion concentration. Also similar to pH, there are no units for POH, so we're going to substitute the value of 6.0 molar into our POH equation without units. And there it is. The POH equals the negative log of 6.0. And now we do the math. Put it into our calculator, and we get that the POH in this case actually comes out to negative 0.78. The rules for significant figures are the same. Because there are two significant figures in the molar concentration of the hydroxide ions, we have two places to the right of the POH. And again, POH is unitless, so there's no unit at the end of that negative 0.78. The negative sign just means that this is very basic, which makes sense because this is a strong base. Now that we've completed the problem, let's think about the answer. Did it make sense? Does it make sense on the POH scale? The answer that we got was that the POH equals negative 0.78. What does the negative mean?